Like, who are you writing it for? Can't even draw it. It doesn't matter. Who's going to read the introduction and who's not? Who's going to definitely read the introduction? Students like you, exactly. So you probably weren't that clear on why you were doing what you're doing until you got squared away to write this. So somebody who was you 2 weeks ago is the audience for the introduction. Somebody who's a real expert in the field might very quickly skim your introduction or skip it entirely because they read the abstract. They already know why it's important. They don't need background. They've got more background information than you do. They might quickly skim through to see which papers you're referencing, but they're not paying much attention to that. They start at the next section down. And so as these pieces go, you want to think kind of section by section, figure by figure, equation by equation. Who would be reading this? So I'm reading it, and I'm like one kind of reader. Your peer reviewers are reading it, but like in a broader sense, whenever you're writing a scientific paper, like why are these the sections that we always have? Why do we always have an abstract? There's a reason for that, and it's because at like a scientific meeting or in a table of contents, just the abstract will appear. So you should have the information in there for somebody who doesn't have access to the rest of the paper right then, but who might be choosing to come hear your talk, choosing to download the rest of the paper, or in the paywall world, choosing to pay $50 to take a look at the rest of your paper. So that abstract needs to have the primary results because you don't want to mislead them. It's your advertisement. That and the title are the advertisement for the paper. Does that make sense? All right. What's the difference between abstract and an introduction? Bing, bing. And so this is for the uninitiated. The introduction is specifically for the uninitiated. The abstract is for the people who already know what you're doing. Essentially, it's a little bit of an advertisement, but you don't want motivation and literature up here unless it's critical to the design of your experiment. Your primary purpose, your method might be we are following the method of so-and-so, and then it is appropriate to put it in the abstract. But otherwise, there are no references in the abstract. Does that make sense? Everybody getting a little sense of that? And this will become more clear as we see. Okay, and the last part I wanted to touch on before we go in, we actually have a lot of stuff to cover today, so I want to zoom, we want to get through, but when we do the peer reviews, this is going to come next weekend. You guys are going to get the chance after everything gets turned in, starting on Sunday, to start doing your peer reviews. The most important thing is stay polite. We're not doing anonymous peer reviews. That started out because Canvas couldn't handle anonymous peer reviews, but actually I think it's sort of nicer in this context because you might go have a conversation with the person. And even when you have an anonymous peer review, you should not be a peer review troll. That's not the goal here. You can be tough, but be respectful that they've exerted a lot of effort. And you might see something that they don't see, or you might have read something they haven't read. That's not a problem. That's an opportunity to improve the work, right? So that's really the goal here. You're taking every opportunity to improve it. Some people think that staying polite means to say things like, looks awesome, or it's really good, or I've got nothing to suggest. That's not really actually being polite. It's not polite to not be helpful. You want to actually give some positive changes that you would suggest. Even if it's as simple as like, this figure, I didn't understand it very well, can you write a better caption? Like, it's not, or they don't have to be, there is a big difference between this paper is wrong and this paper is perfect. We're always in the middle. So you want to be pushing those pieces back and forth and suggesting things you think would make it better. So one helpful comments of this variety are, I really like how you insert something specific. I think you could do better with insert something specific, because it tells them a specific thing to address their focus on when they're revising. This one is also really helpful because the other reviewers might be suggesting something complicated with that, and they might just delete it. So the part that you liked best might go away because they're in revisions, unless you tell them that's the part I like best, in which case they'll make some effort to save it. So does that make sense to everybody? You don't have, and here's another, so once you get the peer reviews back, and this I now have a peer reviewing document to look at, you do not have to take the suggestions that are made. That's not what response to peer review means. You do have to consider them, but you may choose not to do them. There is a category of peer reviewers who loves to give really complicated things to do, like, I love figure 1, could you please do it exactly the same except recalculate everything and put the y-axis on the x-axis and the x-axis on the y-axis, which is just like work, and it's not necessarily going to end up with a better answer. It might be better, but it probably won't, because they haven't thought about it, they haven't played with it. You've already been playing with it before you decided how to plot it. So before you take any major changes, think about realistically, is this worth the effort it's going to take to get there? Because what you've got is functional, they're just offering an improvement. And it may not be an improvement if you think about it. But all of the trivial suggestions, like please define this word, this acronym comes out of nowhere, just do them, just do them all. Like there's no reason, having a separate set of eyes on something, most of those you should just fix and thank them politely for having made them. There will be issues of emotions. You will be grouchy, you will think they don't understand what you're saying. There will be issues of fairness. You will think that other people got really easy reviews and got really hard reviews, you have a lot more to do, or vice versa. There will be time considerations, because we don't actually have a lot of time to do the peer reviews, we don't have a lot of time to respond to the peer reviews. All of this will come up. All of this is just like being a real scientist. So it is a more friendly time to figure out how you do this here in this class than it will be when you are writing papers for peer-reviewed publications. Okay, so that's the goal. That's the reason why we have this. This is an opportunity for you to go through the system, learn how to do it, experiment, get a sense of what it feels like to get peer reviews, which sometimes feel very critical, sometimes feel like really encouraging, whatever. Have some sense of that before you get into trying to write a paper on your own for anonymous peer reviewers who are experts in the field and who are likely to be much more strong-willed and tough about what you're saying. And you might have worked years and then to have the paper get rejected, and it's because of this. Frequently a paper is not rejected because of the first version, it's rejected because of the way you respond to the peer reviews. So you can blow it in that stage too. So that's why we're trying to learn this here, to give you some practice. Yeah.
Just a very trivial question. So in the scientific world of publication, when you correct, when you answer the peer review, do you submit another version to the editor or to another?
So it depends. Most journals give you an opportunity to do some level of revisions after the peer review. But that's not always the case. At very fancy journals, they like to have a high rejection rate because it makes them look good. And so they may just reject if they think that the peer reviews are sufficiently critical. They just say, we can't be bothered with this. They may then say you are welcome to resubmit after you revise, but it's rejected. We're never talking to you again unless you talk back to us. Or they may say you're not welcome to resubmit. That depends. Most journals, not Nature and Science, but typical journals that you would submit to would say minor revisions, major revisions, reject, or accept as is. And outright reject on the first round is very rare, as is accept as is. Though they are possible, they're like fewer than 5% fall into those two categories. Most of them are minor revision, major revision. And roughly minor revision means presentation cleaning up, modest, no new calculations, no new analysis. Major revisions means new analysis, major restructuring of the presentation, unjustified claims, that kind of stuff, pieces you have to deal with. Does that make sense to everybody? Okay, and this will become more clear when we're looking at it. Okay, so we needed to talk a little more about compression and expansion, and then about the seawater equation of state, which I'm going to get to in a second. But okay, so this, I said last time that this is the approximate seawater equation of state. And remember, we have a lot of equations. We have an equation for conservation of mass, an equation for conservation of salt, an equation for conservation of energy that we're going to work on, and then a lot of equations for conservation of momentum, which are going to be complicated. We're going to then, when you add all those up, so you have temperature, salt, salinity, pressure, density, 3 components of momentum. So we've got seven variables we're solving for. And we've got the conservation of mass, the conservation of salt, the conservation of energy, and 3 momentum equations. So 6 equations and 7 unknowns. So we need one more thing in addition to all those equations. And the one more thing is the equation of state. And it's a thermodynamic relationship between the temperature, the salinity, the pressure, and the density. Or there are alternative forms which we could think of too, like energy instead of density. You can swap these around a little. But this is a simplified version of it. And so what it says is density is around some background value, which is around 1,000 kilograms per cubic meter. That's what, for pure water, that's what it is in the absence, if the temperature was equal to some background reference value, then this wouldn't contribute. If the salinity was some reference value, this wouldn't contribute. If the pressure was some reference value, this wouldn't contribute. So these coefficients are empirical, then they're related to what the background values are. So if we said 0 salinity, surface pressure, so atmospheric pressure, and room temperature, then this would be around 1,000 kilograms per cubic meter. Does that make sense a little bit to everybody? Okay, so what does this term do? If the temperature goes above the reference temperature, what happens to the density? Goes down, right? So if this is positive, then this, this coefficient, these coefficients are all taken to be positive, the way this is written. That makes it a little bit less. The density, it's a little bit lighter, a little bit more rarefied when it is warmer. Okay? If you add some salt and raise the salinity above the reference value, what happens? It increases the density. So it gets denser when you add salt. Okay? And then this one is pressure. So if you subject it to very high pressure, what happens? It increases. So it gets compressed a little bit. So since density is mass per unit volume, if you put it under enormous pressure, its volume will decrease a little. And so the density goes up. Okay, so this is a very approximate form of the equation of state, but most of the time you can kind of think of it this way. And a couple slides down, I'll tell you what these values for betas are, and then you can just have them, you can guess. Like if my temperature goes from 30 to 35, how much do I expect the density to change in percentage? That's a calculation you could do easily from this, and it's approximately ballpark right. Does that make sense to everybody? The real one that used to be used was a 72-term polynomial, which has all kinds of nonlinear linkages because how much you warm depends on how much the density changes with warming depends on how salty it is and at what pressure you're at. So it's a really complicated relationship. So though we can keep this one and we'll think this one in our head and it's useful as a kind of exercise, it's not perfect. This is kind of like the equivalent of the ideal gas law for seawater. It's an approximation that's useful to kind of work our way through the thermodynamics, but it's not exact. Okay. Okay, So it's a little worse than that, because that one kind of makes you think you could change the temperature and the salinity and the pressure independently. But that's not actually what happens. If you change the pressure, you take a parcel of water and you push it down to higher pressure, the temperature changes. Oh, I was gonna bring in a bike pump. This is the perfect example. If you pump up a bicycle pump, at the tip, the part where it sprays out and expands, it gets cold. At the point where it's being compressed, the junction between the bottom of the pump and the hose, it actually heats up. And so when you're compressing gases, anyway, it tends to warm up when it's being compressed, and it tends to cool off when it expands. Okay? The same is true of liquids to a lesser extent. Okay. And we can conceptualize that through a conservation principle for something like internal energy, entropy, or enthalpy. Internal energy, entropy we talked a little bit about it last time. Internal energy is how much energy per unit mass there is in the fluid. Enthalpy is kind of a weird hybrid other thermodynamic quantity, which turns out to be actually the most convenient one, but it's hard to imagine, hard to think about it. It's sort of the energy that has to do with heat. Okay? So the equation of state, so if we assume that the equation of state holds and the salinity is conserved following a water parcel, so we're not changing the chemicals are not reacting as we're going from pressure to pressure, then we can think about different flow regimes. We could think about a reversible flow. So if I take the water parcel and I push it down to a pressure and I let it do whatever thermodynamics it's going to do, and then I move it back in such a way that I get back to where I got at the beginning, that's something very special. What doesn't change if I send it down and then bring it back, if I get back to the same thermodynamic state? So the energy won't change, but the energy might not change anyway. But it's really, that's a statement about the entropy. So entropy is like the randomness in something. So if you take like a droplet of milk in coffee and stir it up, that's not reversible. You can't spin the spoon backwards and get it to go back to the droplet. And the reason why is because the entropy is increasing in that forward direction. So this is a special kind of flow that you're imagining if it's reversible. It's a very gentle relocation, neglecting mixing on the way down, neglecting mixing on the way up. Okay? So that's one thing, and if we assume this, then we can assume that entropy is conserved following the fluid motion, and then off we go. We can use that as a conservation law that closes that's the seventh of our set of 7. So there's the equation state plus this one. Or we could assume that it's adiabatic, that is, that the energy is conserved as the flow moves, except for the work done by pressure. So that's like, we just said there's compression and expansion, and that actually does some work. Compression, you're pushing against the tendency of the liquid not to want to be compressed. But you can keep this little piece of the work done, but forget any other kind of thing. So again, it's like there's no viscosity would be an example of a dissipation of energy that wouldn't be included in this. So you're moving kind of quietly down, quietly back, without dragging against anything, without bumping against anything, so that the energy would be conserved, except for that simple work of the compression and expansion. So that's an adiabatic flow. Or you could conserve potential enthalpy, which doesn't mean anything to anyone except people who are really into this. And this is actually a little more accurate than both of these, because this handles a little bit of mixing. So we actually think that this is the closest to what like a quiet fluid motion does as it moves around in the ocean. It would allow for a little bit of mixing of adjacent fluid particles that had similar properties without screwing it up. Okay, does this make sense to everybody? So we're looking for a thermodynamic law. We've got 7 variables. We've got 5 things that are like salinity, temperature, and momentum. We need a equation of state, and we need some kind of thermodynamic law. It could be like the first law of thermodynamics. That's this one. Work is heat and heat is work. Second law of thermodynamics, which is you can't take heat from the cooler to the hotter, but it's also things tend to be irreversible. Entropy increases in most thermodynamic interactions. So if we neglect that entropy increase, we could use this as a limit. Or this one is kind of a hybrid of those two, but this one turns out to be the most accurate. Okay? So all of this builds towards something that we would like to use something instead of temperature. We would like to use something called potential temperature or conservative temperature. And it turns out that these are a pathway to understanding what that is. But once we have potential temperature, we can kind of forget how we got there. So this is a lot more thermodynamics as a motivation, but I don't expect you guys to really understand these bits and pieces because we won't need that level. We just need to know this is the motivating push for why we want potential temperature. Okay? All right. So we can go through this. We can come up with all of these equations. So this is the first. So this is the second law of thermodynamics written in 3 different ways. We can write them in equations with materially conserved stuff and then stuff that's compressive. So this is the internal energy equation. So that's an example of an energy law. So this is like the fluid dynamics version of that. Or we could do it the fluid dynamics version of the entropy equation, which looks like this. So an isentropic flow, so a reversible flow, we just have the entropy is conserved following the fluid parcel. An adiabatic, which is just the energy following the fluid parcels, plus whatever work is done by compression, we just have a 0 over here. So this is an equation for conservation. So the adiabatic change would have a 0 here. The reversible would have a 0 here. And you can see these are both heating Q dots. So it kind of makes sense that they would go together. They're not quite, they turn out to be not exactly the same thing, but they're a very similar kind of slow motion without much interaction with this environment. Okay? All right. So it turns out that there is a thing called the potential temperature. And the potential temperature is such that if you conserve this thing, you automatically recover both of those, the conservation of entropy and the conservation of internal energy. This equation is the same as that. So Q dot, remember, was our source. So this is we get rid of that, and then we would have conservation of this potential temperature. And that's really nice because this looks just like the salinity equation. This just says label every parcel of fluid with its potential temperature and follow it as it goes along. Use our material derivative, the thing we keep thinking about. And so we can grid this up in a model and have potential temperature coming in, potential temperature going out, and rate of change of potential temperature inside the box. We have no complicated terms to worry about. This is great. Okay? So there's a conservative temperature, which is a little bit fancier one, and this is the one that uses the potential enthalpy, which is more accurate than that. But almost no one uses this. This is kind of a new concept which is coming into play now. Oh, and then there's something called potential density, which is very similar to the potential temperature. It's actually the density you get if you use the potential temperature in place of the temperature in the density equation of the state. So that's a related concept. Okay. But either way, whether you're using the potential temperature or the conservative temperature, you get a temperature that's materially conserved. Okay, and if you do this one, and there's no sources, then this would say that internal energy, except for the compression and expansion part, is conserved, or entropy is conserved. It's the same thing for this. So this is an adiabatic isentropic flow that's being described by conservation of potential temperature. And this one is conserving potential enthalpy, which we said is a little bit more realistic. And this is not quite the same as that. Okay? And we don't actually have to even, okay, here are a bunch of equations. We don't actually even have to have, and here's potential density. We don't have to know the equations for these things to talk about them being conserved. There is a relationship, and there is a toolbox in MATLAB or a toolbox in Python you can get that will calculate for you the potential temperature, and it depends on the temperature, which is obvious, it should. It also depends on the salinity, and it also depends on the pressure. Okay? So that's the way we calculate the potential temperature. We just take that function and we apply it to those variables and we get the output. So if you want to convert your temperature measurements from Argo into potential temperature measurements, which we might want to, there's a toolbox that does it. Okay? So looking at those equations is not revealing in this case. So this is where we're a little different this is a little different from the case with the ideal gas law, where they actually have a formula for potential temperature that equals the regular temperature plus the log of the regular temperature. We don't have that. It's not as simple in seawater. So let me go back and show you again. This equation of state, in fact, we could just put the potential temperature in here and do exactly the same thing. To this order of accuracy, in this simple equation of state, it doesn't matter whether this is temperature or potential temperature. The two of them vary pretty much the same way over short distances. Okay? All right, so now let me pause for questions, because I'm about to explain how to think about the potential temperature, and it's a little weird. But before I do that, does everybody understand what the principal idea here is? So why don't we like temperature?
There's no useful conservation law.
Yeah, the conservation law is really complicated because of this compression and expansion stuff. And so we wouldn't be able to do pressure on its temperature on its own. We'd also have to think about energy all the time and whether it was being conserved or not, and entropy as well. Whereas potential temperature looks a lot like temperature. In fact, for small deviations, they're proportional to each other. But for big deviations, they're a little different. Okay? And so we're going to see an example of how where that matters in difference. So now I'm going to explain to you what potential means. So potential is something weird that meteorologists and oceanographers do, where they like to label something in terms of not the value it has, but the value it would potentially have if you followed some thought experiment. So potential temperature is not the temperature of the water at the present location in pressure, temperature, and salinity. That's the temperature. Potential temperature is the temperature it would have if you relocated the parcel in an adiabatic, isentropic way, conserving energy and entropy while you do it, to a reference pressure. Okay? So imagine I go to the surface of the ocean and I say my reference pressure is the surface of the ocean, then the temperature at the surface of the ocean actually is the potential temperature with that reference pressure. But the temperature at 100 meters is not the potential temperature at 100 meters. That would be the potential temperature. The potential temperature at 100 meters would be the temperature that you would get if you took that parcel at 100 meters and moved it to the surface, letting it expand, and if it expands, it does what? It'll cool off, and it does work, both. So it would change its energy a little, and it would change its temperature. So it will have a little bit different temperature when it reaches the surface. That's the potential temperature. It's not the temperature that you measure with the thermometer, but the temperature that's related to that if you relocate that parcel to the surface. Okay? And now I'm going to show you why that's the important one to think about. Okay, here's the thought experiment. And same the way potential density is the density that you'd have if you brought that particle to the surface and let it in an adiabatic isentropic way and then measured its density when it got to the surface. Okay, so imagine we have a background gradient of density where there's some density, there's lighter stuff on top, heavier stuff on the bottom. And then imagine we grab a little blob of water and we push it up. It's going to go to lower pressure, but it's going to conserve something as it goes up. What kind of things would it conserve? Its potential temperature, its potential density, its salinity. If we do it adiabatically, it's energy. If we do it reversibly, it's entropy. So it's going to have a lot of things that are telling us what it does, but it actually will find itself at a different density even though its potential density is the same. Okay? Why does it have a different density? Going from high pressure to low pressure. It's going to expand a little. And when it expands a little, it has this compressive expansion, and that compressive expansion is going to lead it to cool off a little, and it leads its density to go down a little bit. So it's going to get a little bit lighter as it expands, it's going to get a little bit colder. Okay, so here's the problem. Is it going to sink back down, or is it going to keep going? It's gotten a little bit less dense. Has it gotten so much less dense that it's now less dense than its environment and it shoots up to the surface? Or has it gotten, or when it gets there, it's less dense, but maybe it's not as less dense as its environment is less dense, right? Because we're expecting density to go down as we go up and down. Okay, so this is the crazy part. Okay, the potential density or the potential temperature is the one that you compare neighboring parcels. So if I take if I take this up here and I calculate its potential density here, it gets there, it has what kind of potential density? The same, different? The same for potential density. I can compare its potential density to its neighbors. If they have the same potential density, then it's happy when it gets there.
No, if that's the case, the energy is not conserved, right? So moving from.
Yes.
Yeah.
I have to actually physically lift this thing. I might have to push it to get it there. That's true. So, but the thought experiment is the stratification going to work against that or not? That's what I'm after. So if I get this blob and put it up here and the potential density is the same as all the ones up there, is there an incentive for it to move down to here relative to any of its neighbors? No, because I could have just swapped them and I would have ended up with the same, since this has the same potential density as this one and this one, there, I could have just swapped them, and even though the densities would change on both the upward going and the downward coming parcels, they would be the same when they got there, because they have the same potential density. Okay, if I put it up here, and all of its neighbors have higher potential density, so they are more dense, one of the neighbors could go down here and end up being denser than the one that left. So you actually would generate energy like that. So if the potential density increases with depth, it is unstable. If the potential density is constant with depth, it's neutral. You could just swap parcels for free. They don't do any energy. If the potential density decreases with depth, it will be stable. If I push it up, it'll find itself more dense than its neighbors and it would come back down. Okay? The same is not true of density. This is why potential density or potential temperature is important. And you can do the same game with potential temperature. If the salinity was uniform, it would be exactly the same. Then potential density and potential temperature just are interchangeable. But potential temperature and potential density are a little different when you also have salinity gradients to think about. And its potential density is the one that tells you whether you're stable or not. Okay? Everybody seems a little confused. So here's the game. So it is stable if the gradient of potential density with respect to z is less than 0. So that means it's getting lighter as you go up, less and less dense in terms of potential density. Sorry, and this little subscript sigma means potential density. That means regular density. And, well, this little twiddle means background, but we don't have to worry about that. This one, and it is unstable if the potential density is greater as you go up. So that means more dense stuff above less dense stuff. So the heavy stuff in the top is going to tend to exchange and convect. Okay?
So the direction of the depth is kind of reversed. When you close the surface, it actually increases.
So z is always increasing going up. So yeah, it's not depth, it's height. Okay? Everybody's looking a little confused. Let's look at a profile. What?
I just had z backwards.
Yes. So there's this funny thing called the buoyancy frequency N, or the Brunt-Weissela frequency, after Brunt and Weissela, who were the scientists who wrote this down. But it's basically just the negative potential density gradient with some factors out front to give it the units of frequency. And this is related to this. So if n squared is positive, it means that it's stable. If n squared is negative, it means it's unstable, or n is imaginary. But that's actually, so what why it's called a frequency is, suppose I lift this parcel up and it finds itself to be more dense than its environment. I let go. It's going to go down, and then it's going to overshoot. Now it finds itself less dense than its environment. It goes back up. So it's going to just oscillate up and down. So it will form an internal wave, a wave on the density gradient in the interior of the ocean, and it'll just bounce up and down and up and down. This is the frequency at which it will bounce. So this is why it's useful. If it doesn't return back to the beginning, and if it goes up and just shoots off, it doesn't have a frequency. It has an exponential rate of growth. So that's when this is imaginary. It's not a frequency. It's an exponential, rate. Does that make sense to everybody a little? So this is just a useful way of summarizing stability in a unit that matters. Like, who knows what units of density per unit height would be interesting? That's kind of a crazy unit. This tells you, suppose this is 10 cycles per hour. That tells you how stable it is. It's so stable that if I pick it up, it'll bounce up and down every 6 minutes. Like, that's a sense of how stably stratified it is. If it's really stable, it'll go really fast because it'll be restored very quickly by the density anomaly, by the density gradient. If it's really, really moderately stable, it might hang out up for a really long time and just go up and down over the course of very long periods. So this is a more useful units for that concept. Yeah.
What does the frequency look like in the actual ocean?
It's typically 1 to 10 cycles per hour. So it's kind of order of minutes for the upper ocean anyway. And so that would be, in some places, like in California, you can see these. If you're up high enough, you can actually see internal waves coming because they're kind of dark stripes approaching the coast. And you can watch them and time their period, and they'll be order of 6 minutes, 10 minutes, something like that. And we'll get to look at maps of this in a minute. Okay. All right, here are two profiles. These are very nice profiles because they show why potential temperature and potential density are useful concepts. Okay, here is the profile of temperature. Here is the profile of potential temperature. This one looks like this water is warmer than that water, so why wouldn't it just go up and get replaced by this colder water? Exactly. If it goes up, it will expand and cool off, and once it gets here, it will actually find itself colder than the colder water that it appears. The potential temperature takes care of that. This is very moderately stably stratified, but it is still stable, so that the potential temperature is increasing monotonically to the bottom. And then these are, all right, these are the densities. So this is the density based on this is the potential density. And sorry, this is not sigma oceanography to a fun. Since density is like 1,000 plus or minus 3, something like that, they subtract off this part and just talk about this part. So sigma is density minus 1,000 kilograms per meter cubed, just for shorthand. So sigma theta is potential density minus 1,000, and sigma t is the regular density based on regular temperature in this figure. Okay, so here's the potential density, and look, except for that little bump there, it looks like it's monotonically increasing. So this water is more dense than that water in potential density, but look at it in situ density. It looks like this water is less dense than that water. So you might imagine letting it go up there and then it would be less dense, but it isn't less dense because it would expand more so than the density difference, and it would find itself more dense. Sorry, did I say that backwards? It would be, as it goes up, it would expand, it would cool, and it would find itself to be more dense than its neighbors by the time it got up there, and so it would sink back down. And it's the potential density that helps you forget about all that stuff. Okay? So we have a conservation law for potential temperature, and if we plug that potential temperature into an equation of state, we can talk about potential density, and potential density will tell us all about stable stratification, unstable stratification. The only thing it doesn't tell us is, remember, our equation for conservation of mass involves density. That one is the real density, not the potential density. And we would get very, very worried if the variations in density were big, because we would get it wrong. We would be able to conserve potential density but not mass, and that would be weird. Fortunately, we don't have that problem because the density variations are very small, so it's negligibly different to just plug in potential density into the conservation of mass equation. Or even, what do we do with the conservation of mass equation? Remember, it's the one that's v rho dt plus rho del dot v equals 0. We said that if density doesn't change that much, what does this turn into anyway? It is. What goes in must come out. But remember, we had a closely related idea. This. This is the conservation of volume, right? This is the incompressibility law. But we said that actually this is a good approximation to that because this term is really, really small, and this is always non-zero. So if this term is small compared to that one always, and this coefficient is never 0, then you can just forget about that guy, divide through by that, and you end up with this equation. Right? So incompressibility is an approximation to the conservation of mass for things whose density doesn't change very much. But so, since I threw away the term with density in it anyway, it didn't matter whether I threw away a term with potential density or regular density, I just threw away the density altogether, so I don't care. So that's the point. So potential density together with incompressibility is a closed set, and we don't ever have to worry about what the in situ density was at all. Okay? So we'll come back to the equations as a whole set, and you'll start to see how these cancellations work out. Okay. All right. So now I was going to show some profiles of things, but actually I think we're going to start on the other slides and start talking about this. Okay, so, well, Let me see if I have a closing moment with that. Okay. So here was one of our conservation of mass equations. This is the other one. You know, we write out the material derivative and combine them together, and we got this one. And remember, we said that the way that we did what goes in must come out from this was we integrate over a volume, and then this was just the rate of change of mass inside the volume, and then this was this integral over the volume became integrals through the surface by the divergence theorem, and so this is just the stuff carrying the density in and out. So the amount of mass inside goes up and down depending on the fluxes coming through the side carrying their density with them, right? We could play the same game with momentum, so that the momentum coming into a box was getting carried by the fluid that was coming and going. It could bring some momentum in. But it's a lot harder. And the reason why it's harder is because momentum, density, and salinity, which we did the same game for, and temperature, or potential temperature, which now we know has the same game, are all scalars. So they don't have a direction. Momentum has a direction. So when the water comes into the box, it brings the momentum, but the momentum actually has 3 different components of momentum that it's bringing. So you have to write some horrible tensor equation that looks like this, where you've got the flow that's carrying you in, the same as this dot product like this, but then also another whole direction that keeps track of like the direction of the flow that's getting brought in. So this is super complicated. Okay. We have been avoiding the momentum equation for that reason, because this gets complicated. But if we look at the other terms in the momentum equation, like the gradient of pressure, it's not so hard to think about. So we're going to start talking about this equation by not paying any attention to this term at all, because that's the complicated one, and just thinking about the other terms in the momentum equation. But it's a little bit weird because we spent so much time thinking in our budgeting about bringing stuff in and out, the advection of temperature, the advection of salinity, the advection of mass, that when we get to momentum, we're going to not worry about that for a while until it feels more comfortable. Okay? Everybody's looking very confused. Yes, we'll see how it goes. But anyway, all right. So when we look at the momentum equation, we've got this material derivative of velocities over here, and that's the part we've been talking about. So that's like the material derivative of, velocity, or density times velocity is just momentum. So you can put them together and talk about momentum, or you can have the velocity on its own. It's kind of the same equation. You just interact with the conservation of mass to get from one to the other. But in some sense, what we have are a big set of equations. We have an equation that says d rho dt equals stuff. So there's a density, a mass, conservation of mass equation. D salinity dt equals stuff, conservation of salts equation. D potential temperature, dt equals stuff, conservation of energy or conservation of entropy, whichever we choose to think of it as. And then we had the equation of state, which was rho equals rho 0 times stuff. Okay, so how many equations is this? This isn't 1, 2, 3, 4 equations. And what are the unknowns? Density, salinity, potential temperature, and then density again. Okay, so we're all fine, except for the fact, what's hiding inside of all these material derivatives? It's a partial derivative with respect to time plus a velocity. So we need to also know the velocity. So there's hidden inside of these more unknowns. Okay, so how many unknowns are there in the velocity? 3. because there's a velocity this way, velocity that way, and velocity that way. So there are 3 components of that vector. Okay, so we need 3 more equations to close this set. Those are the equations for momentum. So we want to have 3 more equations that look something like d by dt of momentum, or actually, it's just, we just write them out. We just normally write them for the velocities themselves, equals stuff. Okay, so now how many equations do we have? 1, 2, 3, 4. How many is that?
Do you count the one just above the one you're talking about?
Sorry, no, this is just defining the material derivative. It's not actually an equation. How many, so this is sort of a trick. How many equations is this? It's 3, because there's a different equation for each component. So this is repeated 3 times, 1 for each component. So okay, 3 equations, 4, 5, 6, 7 equations. And how many unknowns do we have? We have density, salinity, temperature, pressure, potential temperature. Oh wait, sorry. We don't have potential temperature. And then 3 components of velocity, which you usually write as u, v, and w. 2, 3, 4, 5, 6, 7. All right, we did it. We have just as many equations as we have unknowns, so we have a closed set. So we can solve any problem we want now, except for the fact that we don't know how to handle nonlinear terms like this. So we actually can't solve any problem we want by hand. We need to use computers if we want to try and do this, because some of these equations are really hard to solve. So our progress for the remainder of the semester is going to be thinking about ways to simplify these complicated equations and take them bits at a time. So rather than having all the terms in the equation, maybe we just grab a couple of terms and we can solve those couple of terms, and then we'll actually be able to understand how the system works. If that, say, just like we did for the mass equation, we said, what if this term is really big and this one's really small? We can throw away the small one, just think about the big one. We're going to do that over and over again. We're going to take the full equation and say, what if we just pay attention to just a couple of the terms and forget about the rest? And we'll get approximate solutions that are called balances to that equation. And then that allows us to proceed. And we know that if we do that right, we've got all the equations we need to solve any fluid flow we want. We know everything except for how to solve the equations. Okay? Does that sort of make sense to everybody? So the first example of this I wanted to talk about was the hydrostatic balance. And it's a pressure balance. And just like I said, we throw away all the terms we don't like. This one's ugly, where it's really complicated to even figure out what direction that's pointing. But the hydrostatic balance would just depend on those. Okay. So here is, so what does hydrostatic make you think of? The word hydrostatic.
Water that's not moving.
Water that's not moving. Okay, how do we make water not move in a momentum equation? We set all the velocities to 0. So this term, does it depend on the velocity? Yes, there it is. Does this term depend on the velocity? Yes, twice. But what if we just set both of those to 0? What's left over? This stuff. The other side that doesn't have any velocities in it. Okay? So that's the essence of the hydrostatic balance, is you just take the things that don't depend on velocity and set them equal to each other. Okay? Oh, and let me clarify what I'm doing with these little subscripts. Sorry. In the momentum equation, because there's really complicated directions, I'm just using subscripts to keep track of like which direction goes with which thing. So like a little subscript would be like, it could be the x direction and the force in the x direction, pressure gradient in the x direction. It's just, when these subscripts match, it's just to tell you this term is pointing the same direction as this other term. Does that make sense, everybody? So in this equation, this guy is pointing the same direction as this guy, but not the same direction as this guy. So it's a little bit, it's just a shorthand to make sure that everybody keeps track of where everybody's pointing. You could put a little vector arrow on this and a vector arrow on this, but then you need like a different kind of vector arrow for this guy that's like pointing the other way. It gets really complicated. The subscripts are a little bit easier to manipulate. Okay, so we have the pressure. So let's slow down a little. This is the amount of momentum where? This is density times velocity, so this is the momentum per unit volume. So this is like inside of our grid cell, this would be the one that would say how much momentum is inside your box, right? So if we integrate this equation up over a grid cell, this is the rate of change of momentum inside the box. This one is the momentum flowing in through the sides. That's this. So this is the transport term, the flux term in through the sides. This term is the pressure gradient. Okay, so let's pause for a second about that. Which way do you think the pressure gradient would point? What is a pressure gradient anyway?
It'd probably point straight down because it's the direction the pressure is increasing the most.
Yeah, so it's like a rate of change of pressure. So if we just think of pressure as a thing that varies in space, it's going to point toward the high pressure. Okay? There's a minus sign on top, which actually means it points away from the high pressure, which is a little confusing. Okay? But you're exactly right. It's a force that's pointing from low pressure, from high pressure to low pressure. What is this thing? If it's the rate of change of momentum, what is the rate of change of momentum? Yeah, it's the force. So we often write, Newton's second law, F equals ma, force equals mass times acceleration, but ma is actually d by dt of mv. It's the rate of change of the momentum. So that's what this is. So this is saying we're getting an acceleration because of this thing. So this pressure gradient is a force that could accelerate the flow. So give me an example of where a pressure gradient would accelerate a flow. The wind, for sure. Wind is a complicated one because the Coriolis force is in there. What's like a simple example of like big pressure gradient, stuff accelerating away from it?
Explosion.
An explosion. So if you have an explosion, you suddenly got very high pressure inside the explosion that's moving outward, and all of the air around it is accelerating very rapidly away from the pressure at the center of the explosion. Okay? So the pressure gradient force is the force associated with that kind of pressure gradient. There's also a pressure gradient in the ocean, and that is this kind of pressure gradient, because we're going to get to that in a second. So what are some other forces we might be interested in the momentum equation? What else is fluids on Earth going to experience? Gravity. So gravity is maybe the most important one. So we could just say, forgetting all kinds of complicated other things, this is gravity, this is the pressure gradient, this is the acceleration, and this is the transport, this is the advection of momentum, which is complicated to think about. Okay, but if it's not moving, pressure gradient equals gravity. Or the rate of change of pressure with depth, because if I take this gradient in the direction of gravity, the vertical, the rate of change of pressure with depth is equal to, this is just a way of writing the force of gravity in the right units so that it would be there. Equals minus rho times g. So g is the acceleration due to gravity. So this says exactly what you said. This says the pressure increases, or it actually says the pressure decreases as you go up because of gravity. How fast does it decrease? Well, it decreases with a scale factor of the density. Why is that? Because gravity pulls on massive things more than it pulls on not massive things. So there's a density in there. Okay? All right. So let's think a little bit more. So we could write this way. Oh man, this thing always, I chose the wrong color for this, and then it makes it terrible. It's easy to see, but it's dark. Okay. So the hydrostatic balance is from all the terms we might have in our momentum equation, it just takes these two, the pressure gradient force and the gravitational acceleration, puts them together, it sets them equal to each other. And we're going to come back to this many, many times. How could you solve this? All right, how do I solve this equation? If I know the density, how do I solve it?
Integrate.
You just integrate the z.
All the mass of that.
Exactly, you just integrate. So integral from some level z to some other level z, and that would be the pressure, and or the pressure at one level minus the pressure at another level, and you go, and it turns out to be the weight above you, and weight, so rho times g integrated in z per unit area. So mass times g is weight. This is the weight above you per unit area. And I'm implicitly saying that at this one, this z0, that the pressure is 0 at the surface. You could say the pressure was atmospheric pressure if you wanted, or whatever, but you're going from some constant to some other level in this integral. So how does that, so now tell me, if I start at the surface, and let's just say that atmospheric pressure is negligibly small, and so the pressure is 0. Now I go deeper into the ocean. What does the weight above me per unit area do? It increases, because I'm going underneath more and more water, and that water weighs a lot. It weighs an awful lot, in fact. It weighs 1,000 newtons per cubic meter. Per unit area, it's 1,000 newton meters. It weighs an awful lot. So much so that every 10 meters, I get another atmosphere of pressure. So atmospheric pressure is like a bar. That's like a unit, whatever, 10 to the 5th pascals. Like whichever unit's pressure is so weird. The units are very funny. But like, there's the amount of pressure that's like the amount of pressure like the air we breathe is, like an atmosphere pressure. Every time you go 10 meters deeper in the ocean, you get another atmosphere. So that means that the first 10 meters of the ocean weighs as much as the whole atmosphere above it because of this balance. And then the next 10 meters weighs another atmosphere worth. And by the time you get to 4 kilometers, you're talking about 400 atmospheres of pressure. Okay? But it's all coming from this little equation that's telling us how fast the pressure increases when what two forces are balanced? Gravity? Pressure gradient. There we go. So there are two forces involved. Pressure gradient force, which is the one that comes like from an explosion, and the gravity. And that's the only forces we have in this balance. And this happens primarily in the vertical direction, this hydrostatic balance. And that's the first momentum balance we have. We're going to keep coming back to this over and over again. So the fact that this is a little hazy, this is the introductory version of this. This is going to seem so obvious to you that everything else is going to be like no problem. Okay, here's the way it's going to become more obvious. We can think of a stack of pillows. You know, are pillows very massive? No. Gravity does not attract them very much. We can think of a stack of bricks. Are bricks very massive? Yes. Gravity attracts them an awful lot. But we can also think of the most interesting circumstance where we have a tall stack of pillows that weighs as much as a short stack of bricks. And if you were subjected underneath those, if you were lying underneath a tall stack of pillows or underneath a short stack of bricks, you would have a medium amount of pressure because they would have the same weight above you. And so we're going to use this all the time to think about light water, so less dense water. It's going to be like pillows. You must have a taller column of less dense water or a taller column of less dense air on top of you to get to the same pressure as a shorter column of more dense water. So we're going to jump back and forth between these a lot using the hydrostatic balance to build intuition for how the pressure varies from place to place underneath varying depths of water with varying densities. And it turns out it's a really complicated thing to think about if we just do it from equations, but if we draw it with stacks of pillows and stacks of bricks, it actually is pretty straightforward to figure out how to do it. Okay? And so this is the hydrostatic balance in pictures. Tall stacks of low density stuff could get you to medium pressure. Short stacks of high density stuff could get you to medium pressure because they have the same weight per unit area above you. Okay? So on that closing thought, we're done.